Hello, I'm Sang Hwan-an. I'm honored to be here and to be given an opportunity to share my research with you today at the Code Blue. I'm a security engineer currently working in the Line Corporation, and I'm mostly engaged in application security, such as security assessment, security architecture design and development, and other works related to security. And I like to do bug hunting and exploit as well. In Secure Insight conference in Korea, I talked about bug hunting and some vulnerability that I found, which is able to remote code execution on the major bank. And this presentation is presented in Intertrust and Line Corporation Security Summit in 2017. And Kim Ji-kwon, the private conference in Korea. This is the second version with more content. At this presentation today, I'm going to talk about white-box threat model and also about white-box cryptography as a solution to mitigate these threats. And I will explain how the white-box cryptography works. And then I will move on to attacks that existed in published white-box implementation and my work in commercial white-box implementation. For the last, I would like to share with you some consideration when applying the white-box cryptography to a service. The reason I started this research it seems that people are looking for security of commercial white-box cryptography solutions. Many of academic white-box implementation had a successful attack on them. However, there is no report of a successful attack against commercial white-box solution to date. When I assessed commercial white-box solution using existing attacks, I found out that they were not effective in retrieving the secret key protected. So I eventually modified the side channel attack available in academic literature, and I succeeded in retrieving the secret key, protected secret key. As far as I know, for commercial white-box implementation, this seems the first report that succeeded to recover the secret key. Let me start by introducing the concept of white-box cryptography and white-box threat model. As many of you know, protection mechanism of application security are based on cryptographic methods like TLS, end-to-end encryption, and digital signature, and etc. And cryptographic key is stored in device. Many studies have been shown that finding the cryptographic key is not difficult in application. Since cryptographic keys are directly visible in memory, so it is clear that cryptographic system cannot be safely protected in the untrusted environment. So an attacker have been targeting the endpoint directly using one-day or zero-day vulnerability and phishing attack. Even an attacker has a full control over the endpoint, all data can be accessed. Even if the data is encrypted, they can see the cryptographic key in memory and then decrypt the data. Moreover, the end user might be the attacker trying to modify application to get something for free. Service providers such as Netflix, Amazon Video have used DRM solution to protect its contents, but end user can analyze application installed on his or her device. And they can watch software execution and set breakpoints and modify code and data. Finally, they get cryptographic key and then decrypt the contents. When the attacker has this power, we called it white-box threat model. In the white-box threat model, the attacker can get a binary. They then reverse engineering and debug on cryptographic protocol or algorithm built in binary. And the attacker can control not only cryptographic algorithm, but also all execution environment. There is no limit on the number of attacks. That means the attacker can do everything he wants. Therefore, when we design some threat model for security, we should be aware of white-box attack having superpower. And also, crucial service has to depend themselves at the application level when the platform itself is untrusted. These white-box threat models also include trusted execution environment and white-box cryptography as a solution to mitigate, a solution to protect cryptographic program and cryptographic algorithm and secret key at the application level. In general, hardware-based trusted execution environment, such as ARM-Trustzone and Intel SGX and AMD memory encryption, stores cryptographic key in a hardware-based isolated environment and perform cryptographic operation. It cannot be accessed directly by an attacker, so that it is well known as a solution to mitigate these security threats. However, because of its high dependence on hardware, so it is difficult to apply trusted execution environments on the application services that suit various environments for Android, iOS, and Windows. On the other hand, white-box cryptography is software-based, and it can be used regardless of platform. Okay, then let's talk about white-box cryptography. White-box cryptography aims to protect cryptographic primitive and secret key in software implementation, even when the adversary has a full control to the execution environment and on access to the implementation of the cryptographic algorithm. It combines mathematical transformation with obfuscation technique. So it's not just obfuscation on a data and code level, but it is actually algorithmic obfuscation. In the white-box implementation, cryptographic key are mathematically transformed into something like pre-computed lookup tables, so they're never revealed in a plain text form, even during execution of cryptographic operation. With such a security in the place, it becomes extremely difficult for attacker to locate, modify, and extract the cryptographic key. White-box cryptography is not a new technology in software protection, but it is still attractive enough to direct global attention because it is based on software and may guarantee securing application services on the device and the IoT platform. The first white-box cryptography was presented by Cho in 2002 on the DES and the AES. All white-box AES implementation implementations such as perturbed white-box implementation and dual-cipher masked implementation are based on Chou's implementation. And I suppose that commercial white-box solutions also have improved from the concept of the academic white-box implementation. Well, moving on to how white-box cryptography works. I will be focusing on White-bax AES implementation. Key partial evaluation is one of techniques used in white-box implementation to merge the given cryptographic key with the algorithm. It is an example of such partial evaluation. There are the given key and possible input data 0 to 255. The S-box is recomputed for merging the key into the S-box. You will notice that the value of US-box as T-box in the diagram are dependent on the given cryptographic key. That means cryptographic operation using this table will not limit the key, and we will get the same result as conventional AES implementation. This is a part of T-box for secret key 0xU6C. As you can see, the table size is very hopelessly impractical, but it would help to conceal the original table operations. This is data flow for table-based AES implementation. Let's look at here. It is data flow for round 1 of AES with 0s, 5s, 10s, 15s, the data of the input state after shift row. And we get 32-bit output mapped through the T-box as add round key sub-byte and mixed column. 32-bit output is computed and on exclusive OR utilizing XOR tables so that we get the same result as add round key sub-byte mixed column transformation. And this is an example code. For each round, it operates add round key, sub-byte, mixed column transformation using the T-box, and also exclusive OR operation in the mixed column can be utilized with XOR table. However, obviously, partial evaluation alone is not sufficient for avoiding the recovery of the secret key in the white-box implementation. If the composed T-box from round 1 is known to the attacker, then he can easily recover the secret key. Because he knows all information for constructing T-box, for such reasons, something must be done to protect the contents of the composed T-box if the implementation is going to resist key extraction. I know many of you are familiar with encoding. Encoding is one of the techniques that we can use in white-box implementation to protect the T-box or something like lookup tables. It uses inverse metrics for obfuscating the contents of all lookup tables in the white-box implementation. We suppose A is a square matrix, and we look for an inverse matrix A inverse of the same size, such that A times A inverse equals I. Whatever A does, A inverse undoes. Their product is the identity matrix, which does nothing to a vector. In white-box implementation, by merging a random bijection A along the table, we can create a completely different table. But it is still possible to perform the desired operation if the input data is transformed accordingly by using the inverse matrix A inverse. When performing the operation, the bijection A applied to the algorithm by a new T-box obfuscated and canceled out with the bijection A inverse applied to the data. When you look at the entire data flow of second round of White-bax implementation, data flow of this implementation is similar to the table-based AES implementation, but an internal encoding layer is added. In the White-bax implementation, internal input, output, and all lookup tables like T-box are transformed with various linear and nonlinear bijection, but it is still possible to perform the desired operation. This transformation would be canceled in the next round or next transformation so that the cryptographic operation yields the desired computed result unaffected by the specific bijection. And external encoding layer can be added to protect input and output data outside of White-bax implementation. This is similar to internal encoding. The sender encodes the plaintext with F bijection and passes it to the White-bax. And in White-bax, the encoded input is decoded with F inverse bijection. Then when encryption is finished, ciphertext is encoded with G bijection and passed it to the receiver. And finally, the receiver can decode encoded message with G inverse bijection. And also, pre-computed lookup table like T-box is very huge. Therefore, this leads to the idea of using many small tables instead of just one enormous table. And also, control flow can be obfuscated, making the attacker even more confusing. To summarize, White-bax cryptography is different from conventional AES implementation because key and crypto algorithms are combined, so it never revealed in a plain text form. It is also very difficult to decompose cryptographic key from obfuscated lookup tables. Moreover, since cryptographic operations are also very obfuscated and randomized, so it is very difficult quest for attacker to analyze a cryptographic operation and extract the cryptographic key. Next, I will talk about existing attacks against published White-bax cryptography implementation. There are some possible attacks. You may think that if an attacker knows all interface, something like lookup table construction and encoding method and bijection matrix, key recovery attack could be possible even though all interfaces were obfuscated. Yes, that is right. It is possible. There was BGE attack to retrieve unsecret key by attacking some bijection. The BGE attack triggered a new design of the White-bax implementation. It is uncertain whether BGE attack work or not on the commercial White-bax implementation, but the one thing that I know is that commercial solution vendor developed countermeasure to these attacks to create a new design of White-bax cryptography, but didn't publish the new design. And even if an attacker can analyze all the algorithm and extract the key, since White-bax cryptography can extremely increase their attack cost, something like reverse engineering skill or effort. So I think this is worth it. So with the reason, latest white-box cryptography cryptanalysis has focused mainly on side channel attacks. Side channel attacks have been applied to retrieve the key used in hardware implementation of cryptographic system, but it works on software as well. One of the most powerful and common type today of side channel attacks is the power analysis attack. You may have already heard this attack. In hardware, this attack utilizes information leaked by power supply of a system during a cryptographic operation. Power analysis attack attempt to find a relationship between the power consumption and internal state of the cryptographic implementation. It also allows us to find the cryptographic key that is stored on device. There are 3 steps onto the power analysis attack. First, you need to determine some point to capture intermediate computation value while the cryptographic operation is running, and then capture them. Next, evaluate the relationship between the measured item. Key bytes can be guessed by computing the relationship statistically between the measured item. Actually, power analysis attack in white-box implementation has been proposed by both et al. At CHES 2016 and Simplex et al. At Black Hat Europe 2015. In the white-box implementation, power analysis records intermediate computation data used on the white-box implementation and simulated computation data on the unprotected implementation while encryption operation is running. This is an instant power consumption of a cryptographic device as it performed the AES implementation. When you look at here, the 10 individual rounds of the cipher are clearly visible from the repeating pattern. Power analysis attack, which targets software-based white-box cryptography, correct read-write data as intermediate computation data by using dynamic binary instrumentation such as Valgrind and pin tool instead of measuring physical power, unlike hardware. And then this trace data set is serialized with 0 or 1. For the reference, one of the best things about software-based power model is that we can observe everything without any measurement noise. And after serializing with 0 or 1, compute the correlation between two groups, actual measured trace data and simulated trace data. Simulated trace data can be obtained from an unprotected AES implementation. If an correlation occurs, then there will be highest peak in the graph for the correct key bytes value. There are several types of power analysis attacks, like differential power analysis and correlation power analysis. All of them are possible to extract the key to the white-box implementation. By repeating this process, you can guess the all cryptographic key. And the other possible attack is fault analysis. Typically, an attacker modifies intermediate computation data while the cipher algorithm is running and compare correct and incorrect results to get information related to key. port analysis is able to get the last round key, basically. Then the attacker can use the property of AES key scheduling algorithm that the AES key can be computed if one of the round keys is known. Yes, this is a simple explanation of DFA. Single byte port is possibly injected into the state array after the 9th shift row. Here 0x1e is port and port injected in this example. The injected single port in the state array give 4 errors in the final state. The left side is the port ciphertext with the port, and the right side is correct ciphertext. If you do exclusive OR, port ciphertext and correct ciphertext, you get 4 byte error. After that, you get some possible key candidate from the 4 byte error. So more port ciphertext is required to fully determine the last round key, sorry. And then you can get the last round key from some port ciphertext. Okay, now move on to attacks that target published white-box implementation and commercial white-box implementation. Of course, published white-box implementation can be attacked with the possible attack described above, but commercial white-box implementation is not. Commercial white-box solutions are designed to protect the key used by service provider. Plaintext is the left, protected key is the right. The protected key is encrypted with the master key embedded in white-box crypto engine. To decrypt the protected key, we need to retrieve the master key from the white-box engine. I didn't succeed in retrieving the master key embedded in white-box crypto engine, but succeeded in recovering the key that is protected key used by the service provider. I used correlation power analysis as extension of power analysis. But in order to actually apply CPA in white-box implementation, you need to find a cryptographic primitive to capture intermediate computation value while the cipher algorithm is running. But it requires more reverse engineering skill and effort. Recently, NXP cryptographic researcher Job W. Boss and Charles Swaybain and et al. Presented a new approach to assess the security of white-box implementation which require little knowledge about the lookup table used, nor reverse engineering effort. They made it possible to find the cryptographic primitive without reverse engineering effort by visualizing the control flow of software execution. They used DBI to monitor all instructions trying to read, write, execute some memory address, and record the memory addresses and data being accessed for read, write, execution. And then visualizes the control flow based on recorded trace log. This is a visualization of the open source white-box implementation. The vertical axis indicate the time, and horizontal axis indicate the memory address, and black dot indicate the control flow, and the green indicate read, and red indicates right. If you zoom in, look carefully the entire visualized map, you will find the pattern of round operation. That's a good idea. For AES 1 to 8, you can see 10 round operation pattern. However, it is not easy to find the pattern because the round operation pattern in the entire map visualized is a very small point. There is a disadvantage that the size of the trace log is very huge. That means it takes much time to visualize the trace log. It is a bit tricky, but you can apply CPA after finding the point of the round operation through visualization method. And then I applied CPA against open source white-box implementation. All key bytes were recovered. But what about the commercial white-box implementation? Commercial white-box solution vendors develop more countermeasures to resist side channel attacks like CPA and DFA. But it is still questionable if previous attacks work for the commercial white-box implementation where additional countermeasures are deployed. For now, I will talk more about experimental results against commercial white-box implementation. White-box cryptography solutions have two implementations. There are simple-cipher optimizers for performance and complex-cipher optimizers for security. Because each solution has a different name, so I will refer to it as simple-cipher and complex-cipher. I applied the visualization method and CPA as described above to simple-cipher. If you try visualization methods targeting simple-cipher, you can see this map. Compared to open source white-box implementation, it had a much more complex control flow. Unlike the open source white-box implementation, I couldn't find the round pattern, even though I looked at this whole map, visualized map in detail. Therefore, I thought that visualization is not effective in finding cryptographic primitive in the commercial white-box implementation. So the next thing I thought was taint analysis. Taint analysis is a technique to trace the data flow from some data. It is often used to find vulnerability. For example, if you want to find some vulnerability in a program that can trigger this from user input data, you can use taint analysis to check the data flow of the user input data and find the code that processes the user input data. So I believe that the taint analysis was gonna work in cryptanalysis. In the diagram, take the object A as input value. You can trace all instructions that access object A to check the control flow to object B. I've applied taint analysis to identify cryptographic primitive instead of visualization method, since the cryptographic primitive must access to plaintext or ciphertext. After all, I was able to find the cryptographic primitive by tracing data from tainted plaintext or complex ciphertext in the memory. This is a Taint log from plaintext. From 0x8181ABA, here is the cryptographic primitive of the simple cipher. The amount of log that tainted from plaintext is not so large, so you can easily find the cryptographic primitive. Visualized cryptographic primitive pattern from simple cipher is different from publicly available white-bax implementation. It just looks like a simple for loop. Therefore, cryptographic primitive of commercial white-bax implementation could not be discovered from visualization method. And I applied the CPA to the cryptographic primitive of the simple cipher. As a result, all key bytes were recovered. And then I've applied the attack method that previously applied in simple cipher to the complex cipher. Complex cipher has a much more complex control flow than simple cipher has, and the amount of cryptographic operation is very large. There is no meaningful path found with Taint analysis, but I applied the CPA. There is some pattern in the entire map visualized. I thought that this could be a cryptographic primitive because it looked like one of the tasks in chess 2016 CTF. So I tried to apply CPA, but I couldn't recover the secret key. So I had to find another way. To attack the complex cipher with DFA, we need to know the implementation in detail. But I didn't know where to inject the port, so I thought there was no way other than doing reverse engineering. I looked into the implementation for complex cipher in detail. If you visualize the relationship between the entry point of complex cipher and its subfunction, you can see that it has a very complicated structure. Trust me, it took me a long time to analyze it. I used a Taint analysis to exclude unexecutable code, although I was able to significantly reduce the resource that needed to analyze the implementation, but it was still complicated. When the complex cipher is schematized, it performs an obfuscated cryptographic operation through two functions, function A and function B. Perhaps these functions seem to obfuscate the control flow and perform a cryptographic operation at the same time. These functions also performed something based on tables and repeated so many times that I couldn't fully understand. However, I thought this might be the port injectable point. And I found some tables in the complex cipher, but many tables were not injectable port. It seems to check the integrity of the intermediate computation value. However, I found that some tables were not protected enough. So I injected port simply by flipping one byte in the table. It was not good ported ciphertext, but I saw that something happened from the error I injected. If 4 bytes are exactly effective in ciphertext, it is good ciphertext that can guess the byte of the last round key. I injected single point into many of tables identified through reverse engineering to get a good ciphertext. And I got the many good ciphertexts that were enough to recover all around the last round key. And I was able to get all last round key from good ciphertext. The last round key can make the cryptographic key since it is possible to calculate back the last round key through key scheduling algorithm. In conclusion, I have found that commercial white-box implementation was not perfect as the published white-box implementation. Even so, I still believe that white-box implementation is a good solution to protect secret key and cryptographic program for application. And also, using white-box cryptography to protect cryptographic key is still better than using unprotected cipher algorithm. And also, commercial white-box solution is more powerful than published white-box implementation, and cost performance is clearly better. So we are now adopting commercial white-box cryptography to protect cryptographic key. Talking about some consideration when applying white-box cryptography to a service, generally, it is almost the same as secure crypto coding rule. For example, do not use single key and do not use hard-coded key, and do not use static initial vector. External encoding described above could be added to mitigate side channel attack, such as power analysis and fault analysis. It is encoding applied at the input and output of the cipher. Both input and output encoding are assumed unknown to attacker. In such an environment, power analysis cannot be directly applied because the attacker is not able to predict the intermediate computation value processed by the cipher implementation. Similarly, if output encoding is applied, an attacker cannot observe the exact effect of fault introduced in the execution of the cipher. Therefore, DFA attack on encoded output is not feasible either. However, I do not recommend depending only on external encoding because external encoding is just one of mitigation techniques. And the side channel attack I used is easy. When the key is always the same. If the key is updated every time, the side channel attack will be very difficult. So it is safe to update the key frequently, whenever possible. White-box cryptography is not all-in-one solution, so you should apply the white-box cryptography to your service while keeping the common cryptographic rules. And commercial white-box solution vendor have white-box design for the other algorithms, such as RSA, elliptic curves, Differential, and more. So it is good idea to update or exchange the key every time using a symmetric crypto algorithm based on white-box implementation. In order to use white-box cryptography more securely, commercial white box solution vendor providing some features such as device binding and tamper resistance function. Attacks such as DFA can be mitigated by checking the integrity of the code and data. If you can enable integrity protection among the tamper resistance function, you have to enable it. Cryptographic key used in commercial white box implementation is protected, but attacker can extract the protected key in a plain text form. They can copy the key and paste to themselves in their environment. So there is additional security layer by binding the keys to specific device so that they cannot be imported on any other device. Cryptographic key bound with some identifier like Android ID, user ID, and customized ID is working only on specific device. That means even if attacker takes the protected key, it cannot be used for his device. Sometimes, because the attacker could obtain the device identifier, so external data-based binding can be used, which can get from external source like pin code or camera and microphone. For example, you can bind cryptographic key to specific device with user's pin code and device identifier, or bind the cryptographic key to the device with the device identifier and user's biometric information, which is obtained from the camera or microphone. There is touch extractor that convert biometric data into some static data. It is possible to make some key from biometric information. You can use this key as biometric identifier. I'm currently testing for biometric binding, but there is a lack of research into biometric binding in the area, and the idea above have not been extensively tested nor verified. So we need to look at this in more detail and further study. Well, I have some interesting projects for myself in the future. The one thing is I would like to make something like white box extension for crypto libraries such as OpenSSL, TomCrypto, and etc. But there is some compatibility issue. So in the near future, I'd like to show you what you can actually use. And the other one is, as you know, I didn't succeed in retrieving the master key embedded in white box crypto engine. So I will focus on getting this master key in the future research. And you may be aware, vulnerabilities I found were already fixed. So, and there are many types of cryptanalysis methods, such as collision attack and the other thing. So I'm gonna try to retrieve the key with the other vulnerabilities. Okay. Well, that is all from me today. I hope that my presentation helped you to apply white box cryptography to service securely. So I think it may be difficult to understand all in an hour. So if you have any question, feel free to contact me by email and Twitter and Facebook privately. I will be happy to answer any of your questions. And also, it was not easy to disclose our key recovery attacks because there is some legal issues. So just for the notification, I may not be able to respond to sensitive question. I'm sorry. Anyway, thank you very much. Thank you for listening.